Let's learn about resonance and polarity. This is our last lesson in the drawing covalent compounds subunit of 8B. We're going to be on pages 136 to 137. Now, in order to be able to do this, you first have to know how to draw compounds. You need to understand when to place sigma and pi bonds. And so if you don't know how to do that yet, you need to go back and watch those prior videos. And then this is the last little bit of understanding what we have drawn. Okay, so today we're going to focus in on the concepts of resonance and polarity. Resonance is something that we've already talked about before. Resonance is when we draw a compound and we get to choose where we place the pi bond. So let's say that there's, say 3 oxygens in this case that are bonded to the carbon, and we need to make a pi bond in order to satisfy carbon's octet. We could choose the top oxygen or the bottom right or the bottom left. And any of those would be correct. Because there are multiple options, that's what we call resonance. In reality, it's not any one of these options, it's all of them at the same time. The molecule is kind of like a hybrid of any of those, but that's what resonance is. It's just showing the possible placements of a pi bond. There's more than one place that that bond can go. And so in this case, this molecule had 3 resonance options because there were 3 possible drawings. Now you may note that this looks a little different than what we've been doing before. That's because we drew a compound that was a polyatomic. And so I want to just remind you or verify for you how we calculate the electrons. Everything else is the same. But if we have a polyatomic ion and we have a charge given in our formula, we have to do the opposite of our charge when we're counting those valence electrons. So for example, this was CO3 and it was -2. So I had 4 for carbon plus 6 times 3 for oxygen, and then a charge of -2 means we've actually gained 2 electrons. And so that's why I add those 2, and that would give me a total of 24 electrons. If I had NO3 and let's say it was a +1, then I would do the math, and so that would be 5 plus, I would do the 6 times 3, and then since it was a +1, I would do the opposite of that, because a +1 charge means you've actually given away an electron, so I would subtract that electron out of my count. And then I just draw them like I normally would. So that's what resonance is. Not all molecules have resonance, they only have resonance if there is more than one possible placement of where we put a pi bond. Now, all molecules do have polarity, and so I'm going to zoom in a little bit here for polarity. When we talked about polarity before, we talked about polar and nonpolar bonds. In a polar bond, the electrons were shared unevenly, and so one side of that bond got a little more of the electron, and it formed what we call a dipole, or a slightly negative charge. And the other side, since it had less of that electron that it was sharing, got a slightly positive dipole. We can also look at molecules as a whole and look at their polarity. And again, it has to do with whether or not the electrons are evenly distributed and shared, or if there is a side that ends up with more electrons than the other. So when a molecule is nonpolar, those charges or electrons are kind of distributed evenly. There's no one side of the molecule that has more electrons than the other. We're always focusing on the central atom. So we look at the central atom, we look what's around it. We can see in this case that it looks the same all the way around. So we're going to say that's a nonpolar molecule because there's no side that has more electrons than the other. If we look at this, same thing, we look at our central atom and it looks the same all the way around carbon. Therefore, it's a nonpolar molecule. If something is polar, that is a not evenly distributed electron, so there is a pole of charge, a dipole that forms in that molecule. And so we remember if polar means sides, then a polar molecule has electrons more on one side than the other. Anything that has a lone pair automatically is polar because those lone pairs are not being shared between atoms, and so they really have a negative dipole. So I can see automatically this does not look the same all the way around, so that's going to be polar. Same thing here, it doesn't look the same all the way around, so it's going to be polar. But even something like CH3F is going to be a polar molecule because there's a grouping of electrons that's occurring over here that is not occurring anywhere else in our molecule. So if we were to practice this, I'll do the first problem on page 136. I'm going to slide that over. We're going to do the things that we always have done. Then we're just going to say whether or not there's resonance for the molecule, and then we're going to talk about the polarity. So when I go to do this, I'm going to go ahead and write that I have CO2 has a -2 charge. So when I do the math, carbon has 4 valence electrons, oxygen has 6 times 2, and then I'm going to add 2 more electrons because of that +2 charge. So that gives me a total of 18 electrons. I'll place carbon in the middle and put an oxygen on either side. Each of those sigma bonds counted as 2 electrons. So now I have 14 electrons left over. I'll go ahead and put 6 on each oxygen to satisfy its octet. That leaves me with 2, and so I'll have to place the 2 as a lone pair on carbon. Since I have a lone pair, I automatically know I'm going to have a polar molecule. Now I go in and I check. This oxygen has an octet and this oxygen has an octet. However, carbon only currently has 6. So I have to cross out and share. So if I cross out on this side and share, that gives me one of my possible options because I could have also crossed out from the other oxygen. So before I move on, I'm going to make sure that since my compound was in brackets with a charge, my picture is in brackets with a charge because I need to show that this picture has 2 additional electrons. And then I'm going to say, but it could have also been, and then I just draw it again. But this time I show the double bond or pi bond on the other oxygen. Okay. Now, just because it's in brackets and has a charge does not mean that it'll have resonance. But if there is more than one location where you could put the pi bond, it has resonance. And so we would say that this has 2 resonance options because we could have used the oxygen on the left or the oxygen on the right. In reality, it's not this one or this one. It is both of them at the same time because you kind of get a hybrid model of the 2. Now, when I look around the central atom, I see a lone pair. As soon as I see a lone pair, I automatically know this is going to be a polar molecule because the charge is not evenly distributed around the central atom. And so for the remaining compounds there, you're just going to draw them like we've been drawing them. If there's more than one option, you're going to show me and you're going to tell me how many resonance options there are. And then you're going to look at the polarity. If the electrons are evenly distributed all the way around, we would say nonpolar. But like we can see here, we've got bond, bond, and then lone pair. That's going to make it polar because it's not going to be the same all the way around. And that is resonance and polarity.